Hey, ladies and gentlemen, we are starting today learning about the one sample t-test for paired data. That's what your homework will be about. And then I also want to teach you guys the one sample t-interval for paired data so you're familiar with both of them. Let's get going right away and not waste your time. Investigators at the U.S. Department of Agriculture wish to compare methods of determining the level of E. coli bacteria contamination in beef. Two different methods, A and B, of determining the level of contamination were used on each of 10 randomly selected specimens of a certain type of beef. The data obtained in millimicrobes per liter of ground beef for each of the methods are shown in the table below. Lots of words there, guys. Deep breath. What you can see in the table is you can see each specimen. There were 10 specimens, and both methods were used on each specimen. When a subject or a unit gets both treatments, that is matched pairs experiment, which means our t-test is going to be a little bit different. We still only have one sample, but what was happening with that one sample was two things were happening, and we're going to investigate the average difference between those two things on that one sample. That's really important to notice that sample because eventually we're going to have a two-sample t-test, but it's not paired data that time. Why? Because it's not a matched pairs experiment. So it's really important to key into one sample right now. Two things are happening to each unit or individual in that one sample. It now says, is there a significant difference in the mean amount of E. coli bacteria detected by the two methods for this type of beef? Provide statistical justification to support your answer. On the AP test, unless they tell you to construct an interval, you can assume when they say, is there a significant difference? Provide statistical justification. You're doing a test. Now, that's not to say you won't get credit if you did an interval here, but know that they will ask you to do an interval because so many times I get, when do I do an interval versus when do I do a test? They will say construct an interval when it's time to construct an interval. If they just say, is there significant evidence? That's a test. Please don't just answer yes on your free response question. I did have a student do that one year. They said, is there statistical evidence? And that student just wrote down yes. Okay, let's get started. In our state, everything kind of stays the same on what we've been doing. I want to get a different color. When we state here, over here, I want to state, oh, it didn't come out different color. That's okay. The parameter, we are dealing with a mu, and we're actually looking at the true mean difference in the amount of E. coli bacteria detected by the two methods for this type of beef. Okay. Now, when we have paired data or a matched pairs experiment, our null hypothesis is always the difference is equal to 0. Always, unless something changes, but I anticipate it won't unless it's a number 6 question, which we'll talk about later on in the year. So again, paired data, matched pairs experiment, we assume that there's no difference. In this case, we're looking just to see, is there a difference? It doesn't say if one is greater or less than the other, like there was in our homework, that number 4. Okay, in this one, they just want to know, is mu not equal to 0? I know I can type it out, I just don't like how it looks. So that means there's a difference. Okay, we're looking to see, is there a difference? Our alpha level will stick with 0.05 unless they tell you something different. Okay, next what you see for the plan, instead of a RIN, I have PRIN. And I did fail to talk about this because I went so quick when we went over that number 4 in class, so forgive me on that. That P stands for, and I'll put it over here as well, P equals paired data. So we're going to acknowledge that we have paired data, okay? R stands for randomization. Is there anything random? Randomly selected specimens, okay? So I want to make sure I'm spelling right, specimens. Okay. Now, this is different. We're not going to do that 10% rule anymore. Okay. When we have a matched pairs experiment, this data is actually not independent of each other, but what we say is we say responses are independent of each other, okay? Okay, so that's new learning here. The paired data part is new learning, as well as the I. The responses are independent of each other. Again, I spelled it wrong, forgive me. Again, new learning there on the paired data, and then that I, responses are independent of each other, and that's all you have to put there. And then finally, our normal condition is the same. So what we need to look at is we have to have an action step here, okay? We have to have an action step here, and there's a reason for that. For our N, ladies and gentlemen, we are dealing with means. We are still wanting to know that our sample size is greater than or equal to 30. Well, our sample size is not greater than or equal to 30. It is 10 here, I believe, right? Yes, 10. 10 is not greater than or equal to 30. But remember, the T distribution is robust, which means that we can proceed as long as the data that we're looking at when graphed is somewhat symmetric with no outliers. In this case, why does it need to be somewhat symmetric? Somewhat symmetric because it's considered the small sample. If you go back to the couple videos before when I talked about my medium sample versus my small sample, the medium sample can have some skew with no outliers. So what am I going to have to graph? Well, I'm going to show you right now. To get set up to look at the graph of this data, the first thing that we need to do is we need to put L1 and L2. So L1 is going to be our A, L2 is going to be our B. I want you to pause the video right now and I want you to type that into your calculator. If you've forgotten how to get to L1 and L2, you go to Stat, you hit Enter on Edit, you scroll up and make sure you delete your L1 and your L2. I'm sorry I said delete. I'm pressing the clear button. Please don't delete it or it will go away. I can help you get that back easily. I can even make a little video on it. But let's go ahead and let's pause our video right now. I'll do the same and enter our data. All right, ladies and gentlemen, so I have my A data in L1, my B data in L2. Okay, the next action step that we need to do, again, this is new learning. We need to go ahead and we need to go to L3 right now. Okay, so I'm going to scroll up and I want to scroll up and I want my cursor to be on L3. Okay, again, I want my cursor to be on L3. Now, they didn't define here about which difference you should look at, B minus A or A minus B. It really, to be honest, in this case, it doesn't matter. In our question number 4 on our homework from the previous lesson, that did define it. And you'll see that in the homework. Sometimes they'll tell you how to define your data. Like we want to look at the post-test minus the pre-test. That's a common one. Or sometimes they look at weight loss regimens and they want to look at the ending weight minus the beginning weight, or the beginning weight minus the ending weight. Like they'll set it up for you. In this case, it doesn't matter. I'm going to just take a glance at it. I don't see, they look very similar. So I'm just going to take L1 minus L2. Sometimes I like to set it up where I'm going to have more positive values. But here it looks like it could go either way. I just talked a lot at you, but what we're looking at is we're looking at the differences here. So I'm going to put this in L3, the differences. We could go ahead and calculate this by hand, but why would we do that when our calculator, second 1 minus second 2, can go ahead and do that for us, okay? And you can look like I got mostly positive numbers there, which is nice. I like working with positive numbers a little bit more, but again, doesn't matter. Now, all I care about, ladies and gentlemen, is this L3 column. Okay, why do I care about that L3 column? Because I want to see, we know right now that 10 is not greater than or equal to 30. So I want to see a graph of those differences. And I want to make sure that it's somewhat symmetric with no outliers. So you can see I have plot 1 set up as on. I have my box plot with outliers showing, so I don't have to calculate my outliers by hand. But what I need to do is I need to change my X list to L3. Because that's what I'm looking at. I'm looking at the differences. I care about the mean difference from method A to method B. I'm going to go ahead. I'm going to hit zoom 9. And you can see there is a slight skew there, which is a little uncomfortable. But what we can do to confirm that it's okay is I'm going to show you the probability plot. Okay, I'm going to show you the probability plot. The good thing is here is there are no outliers. Again, I do have a slight skew. We can make an argument that it's somewhat symmetric if I go to second y equals and I show you a new plot. Right here, this is called a probability plot. Let's go ahead and let's look at that probability plot. I know Mr. Jans has taught this to some of you. I am going to look at L3. I'm going to leave everything else here the same, and I'm going to hit zoom 9. Sorry, I must have something in my y equals right now. That's why there's a line here. This plot right here, and I got this from the College Board, actually, this problem. This plot is straight enough. When we look at a probability plot to confirm normality, we want that probability plot to be somewhat straight. Again, I'm sorry, I have a y equals in here, and that's why that showed up. So let's go ahead and zoom 9 so we don't see it. We can make an argument that this is linear or straight enough. And we can say, okay, we can proceed because that probability plot is straight enough with no outliers. Okay. Again, we could have looked at the box plot. We could have said symmetric enough. I know that's uncomfortable for those of you who are diehard calc people to say it's good enough, but we can do that in statistics. So right here, I'm going to say the probability plot is straight enough. It's okay to proceed. We know there are no outliers. How do we know that? Because we checked on that box plot with those outliers. Again, it's okay to proceed. What was the new learning in this plan step? The new learning was the paired data piece, the independent piece, and then learning about that probability plot that the data, as long as it's straight enough, we're okay to proceed. Let's go ahead and let's go to the do part. Ultimately, what I'm going to be grading on the do part is the t-score, the degrees of freedom, and the p-value. I'm going to go to the board right now for the do because I want to set up the sampling distribution of the statistic, that model. Oops, I got to plug it in. I don't see it. Give me a second. Thanks for your patience. Come on, let's get it on. Here we go. Okay, so when we're looking at this, guys, we want to make sure that we have our curve. Pull this down. In the center, we have our mu. Our mu is equal to 0. This is always our null hypothesis, ladies and gentlemen. Next, I have my standard error of the statistic. We know that's that sample standard deviation divided by the square root of n. We don't know the sample standard deviation yet, but we do know that it's going to be divided by the square root of 10. I know I'm going to go to my calculator. I could do a one variable statistics to find that out, but I'm going to go ahead and I'm going to run the t-test right now. Excuse me. Let's go ahead and let's go to the calculator. Stat, arrow over to test, go down to t-test. We have data. We do not have statistics. Okay. Our null hypothesis is 0. The list of the data that we care about is list 3. So second, 3. Our alternative hypothesis, frequency, leave it as 1. Our alternative hypothesis is a not equal to. I'm going to go ahead and I'm going to calculate. Bring my screen over because that's just so fancy. Okay, so what am I looking at here, guys? I see right here, this is my sample standard deviation. That's the standard deviation for the 10 differences there. So I'm going to put 0.6297 divided by the square root of n. I know that the mean difference for those 10 specimens, right, the 10 meat specimens, that is going to be right here, 0.29. That was the difference between the A and the B. So x bar is equal to 0.29 over here. I'm going to shade to the right. This is two-tailed, so I'm also going to shade to the left over here, approximately the same area. Next, I need to find that t-score. Just like we said zoms before, now we're dealing with toms. Okay, t is equal to our observation. Our observation, you guys, that's our statistic right here, what we observed, 0.29. So O is observation. M is minus my mean. Minus my mean is 0. Divided by my standard deviation, 0.6297 over the square root of 10. In this case, it is the standard error. That t-score then they give us is right here. at 1.4563. What am I grading on your test? I want to see this work right here with the correct t-score. Next, I want to see what our degrees of freedom are. Our degrees of freedom is still n minus 1, okay? So that's 10 minus 1 is equal to 9. So I want to see that. And then finally, I want to see my p-value, and that is right here. My p-value is equal to 0.1793. Okay? That's what I'm going to be grading on the test for the do part. We're done with the do. We have our t-score, our degrees of freedom, and our p-value. What is this setting us up for? This is setting us up to saying, do we have evidence that there's a significant difference? Remember, ladies and gentlemen, we want to compare our p-value to alpha because our p-value, 0.1793, is greater than alpha, 0.05. We fail to reject the null hypothesis. We have no evidence that the true mean difference in, okay, where is it? Let's look. I want to make sure I have it right. I'm going to just copy it here. The true mean differences, Control C, Control V, in the amount of E. coli bacteria detected by the two methods for this type of beef is not equal to 0. We have no evidence that it is not equal to 0. Okay, the double negative feels weird and uncomfortable, but just get used to practicing p-value is greater than alpha, fail to reject the null hypothesis, no evidence for the alternative hypothesis. We have that all down in our notes from previous videos. Make sure you have that down. At the end of the video, I'll do a quick recap on how do I know if I reject or fail to reject if you need that. We're done with the test. Take a break if you need it. In fact, I'm going to stop the video right now and I'm going to do another video on the interval.